In this skill, we're going to be putting together what we know so far about Gibbs free energy, along with what we know about enthalpy of formation, to figure out our Gibbs free energy for a reaction. So we're going to be provided with a table that contains the standard enthalpy of formation and the standard molar entropy for each of our compounds. And we're going to be using that to figure out the enthalpy change of our reaction and the entropy change of our reaction. And then we're going to be using that in the Gibbs free energy equation to figure out our change in Gibbs free energy and whether our reaction will be thermodynamically favorable or not. So in this particular question, a scientist wants to predict the change in Gibbs free energy, delta G naught reaction, for a fictional reaction involving fictional elements with the symbols T, Z, Q, and X at 660 Kelvin. Our first step is going to be balancing our equation. I'm not going to show how to do that here. I'm going to assume you're already confident with that. If you need more practice, head back to the balancing equations unit. So to balance this, I need 2 of this, 1 of this, 2 of this, and 2 of this. Okay, my next step is to figure out my enthalpy change of reaction. Here's my equation for the enthalpy change of reaction. The enthalpy change of our reaction is equal to the sum of the enthalpy change of formation of our products minus the sum of the enthalpy change of formation of our reactants. So the enthalpy change of reaction is equal to the sum of the enthalpy of formation of our products minus the sum of our enthalpy change of formation of our reactants. So the enthalpy change of formation of our products. So in our products, we've got 2 sets of T2. So I've got 2 sets of that. And I've got 2 sets of X2ZQ3. So that's going to be 2 sets of negative 21.5 plus 2 sets of negative 68.6. Then I'm subtracting from that the total enthalpy change of formation of my reactants. In my reactants, I've got 2 sets of T2ZQ3 and I've got 1 set of X4. So that gives me 2 sets of negative 50.9 and 1 set of negative 34.5. So if I put that all into my calculator, I'm going to get an enthalpy change of reaction of negative 43.9 kilojoules per mole. So we can go ahead and fill that in over here, negative 43.9 kilojoules per mole. Then we're going to do the same thing for our entropy. To find the entropy change of our reaction, we're doing delta S naught reaction is equal to the sum of S naught of the products minus the sum of S naught of the reactants. So for our products, we had 2 sets of T2. The standard molar entropy for T2 is just 0. So 2 times 0. Plus we had 2 sets of X2ZQ3, which has a standard molar entropy of 265.0. Then we're subtracting for our reactants. We've got 2 sets of T2ZQ3, which has a standard molar entropy of 258.5. Plus we have 1 set of X4, which has a standard molar entropy of 0. So if we put that all into our calculator, we're going to get a entropy change of reaction of 13.0 joules per Kelvin mole. However, we need that to be in kilojoules per Kelvin mole. So let's do a conversion. We're starting with 13.0 joules per Kelvin mole. And remember, 1 kilojoule is equal to 1,000 joules. That's our conversion factor because kilo means 1,000. So I'm going to put joules on the bottom so that will cancel out and kilojoules on the top. And we know that 1 kilojoule is equal to 1,000 joules. So we're going to multiply everything on the top and divide top by bottom. The joules will cancel. we're left with 13.0 times 1 divided by 1,000, and our units are kilojoule per Kelvin mole. And when we put that into our calculator, we get 0.0130 kilojoules per Kelvin mole. So we can go ahead and enter that in over here now. 0.0130. Awesome. Okay. Next, our temperature that was given in the question as 660 Kelvin. Awesome. So now we just need to use our change in Gibbs free energy equation. Here it is, Gibbs free energy, enthalpy, and entropy equation. The change in Gibbs free energy for a reaction is equal to the change in enthalpy minus temperature times the change in entropy. Remember, temperature must be measured in Kelvin. So we've got delta G naught for a reaction is equal to delta H naught for our reaction minus temperature times delta S naught for our reaction. So let's go ahead and put in our numbers since this is already arranged for delta G naught. Delta H naught was negative 43.9. We're subtracting the temperature, which is 660 Kelvin, multiplied by the change in entropy, which was 0.013. So we've got delta G naught is minus 43.9. And then we're subtracting, I'm going to put in my calculator 660 times 0.013. That gets 8.58. So finally, if we put that all into our calculator, we're going to get a delta G naught of negative 52.5 kilojoules per mole. So we can fill that in here. Awesome. So we found our delta G naught of reaction. Next, we're asked what drives this reaction. Now remember, to drive a reaction, something has to help to make delta G naught more negative. So either that's going to be delta H naught being negative, or since we're subtracting T times delta S naught, if delta S naught is positive, it then gets subtracted to make delta G naught more negative. In this question, we have a negative for our delta H naught, and we have a positive for our delta S naught, making that term negative. So both the enthalpy and the entropy are contributing to driving this reaction. So the answer here is both enthalpy and entropy. And we can fill in our answer here. The change in Gibbs free energy was negative 52.5 kilojoules per mole. Finally, we asked, is the reaction thermodynamically favorable and is it spontaneous? Since our delta G naught is less than 0, that is telling us yes, it's favorable and yes, it's spontaneous. So overall in this question, first we're using our enthalpy change of reaction in terms of enthalpies of formation and our entropy change of reaction in terms of entropy of formation, along with the data in the table to figure out our enthalpy change of reaction and entropy change of reaction for this reaction. Then we're just putting that all into our delta G naught equation, exactly the same as we have in the previous skills. And again, if delta H naught is negative, that's helping to contribute to delta G naught being negative and helping to drive our reaction. If delta S naught is positive, that's helping to drive our reaction. And finally, if our delta G naught is less than 0, that means it's thermodynamically favorable and spontaneous.